Hello there, it's Steve Giles for the next lesson of Cambridge International Education IGCSE Physics, Unit 3, Waves. Today we are looking at ultrasound, and I want to describe the applications of ultrasound, and I suppose also what ultrasound is. So, quick recap from the previous lesson on sound. What's the range of human hearing? Well, it's between 20 Hertz and 20,000 Hertz. So that brings into today's lesson, which is what is ultrasound? Well, it's above the range of human hearing. So it's sound with a frequency above 20,000 Hertz. So is it transverse or longitudinal? Well, it's the same as sound, so therefore it is longitudinal. There's some applications. You can use it for cleaning. Okay, so you've got like a machine here, and it's got a fluid inside, a liquid, and the liquid is given a pulse above 20,000 Hertz, and they vibrate very quickly, and they vibrate the particles off the dirty object, wherever it may be. So very quick, this is a GCSE paper from the UK question. So the ultrasound generator makes molecules of the cleaning fluid vibrate. The molecules knock particles of dirt, muck, grease, rust, etc. From the surface of the jewellery. Seconds. Okay, then ultrasound waves can be represented on the screen of a cathode ray oscilloscope. The diagram shows 3 ultrasound waves. Each wave is represented on an identical screen, A, B, and C. How many complete waves are shown in B? So it starts here, goes up, comes down, goes back up, that's 1. Goes down, comes back up, that's 2. And which screen shows the waves the highest frequency? That's the one with the most waves. So that would be screen C. Okay, so that's a fairly simple GCSE question from the UK. Now, applications, which is what we're really focusing on today. Another one is removing kidney stones. Okay, so kidney stones are basically large things that are like stones, I suppose, that build up inside kidneys, and they can't pass through easily. Okay, so they can't actually pass out through your urine easily, like a lot of other waste products. So ultrasound, 2 seconds, move that away. Ultrasound shock waves crush the stones, make them much, much smaller, so that it can pass out of the body in urine, although I can imagine it's still a little bit on the painful side when it comes out, but certainly much more doable than the original size of the kidney stones. You can also use it for fetus imaging. So this here is an ultrasound scan. Now, if your parents might even have one still when you were inside your mother's uterus. So this here is a GIF of an ultrasound. When the density of a medium changes, some of the ultrasound is reflected back. So, for example, when it goes from the fluid inside the uterus to hitting skin, muscle, bone, etc., some of it will be reflected back. It is not ionizing, so won't harm the fetus. This is used for fetus imaging, as unlike X-rays, ultrasound can't cause cancer, so it's not ionizing. It's normal for an adult to have X-rays. However, if you have, a fetus is still developing, so they're a lot more susceptible to radiation poisoning. Ionizing radiation. So the last thing you want is to be given an X-ray to a fetus, because it could cause birth defects. One other thing to mention is to send a signal with something called a transducer usually. Now that transducer acts as both a transmitter and a receiver. So it'll send a signal and it'll wait until a signal is received and kind of works out how deep it is by timing how long it takes to travel a certain distance and for it to then be received. And it will sort of know the speed of ultrasound in various different mediums because it'll travel at different speeds in different mediums. Okay, we're going to use for seabed mapping. So in water, ultrasound travels at around 1,600 meters per second. It will vary a little bit. The distance to the bottom of the seabed can be calculated using distance to speed times time. So you've got a transmitter and a receiver, or like I say, you can use a transducer, which will be a transmitter and a receiver rolled into one. Most of the ultrasounds reflect when it hits the seabed. The time it takes for the reflected wave to return to the receiver must be half to get the time it takes to reach the seabed. So, for example, if it takes 2 seconds for the transmitted signal to be received, then that means it took 1 second for it to hit the seabed and another 1 second to be received. So the distance will be speed, 1,600 times 1, which is 1,600 meters, which would be quite deep at that point. Okay, so this here is just a little summary of everything we have just talked through. You can take a screenshot of this if you wish and use it to help you with our paper 2 questions, which we're going to have a look at now. So ultrasound has many uses. For what are ultrasound waves used? Out of these, they are used they don't kill cancerous cells, they're not going to give you a suntan, and they've got no use at the minute they're not used in telephones. So it's used in prenatal scanning, so fetus imaging. What is ultrasound? So let's have a look for the definition. We'll start from the bottom. Sound waves that are too quiet for humans to hear. So that is related to the amplitude, which is not relevant to ultrasound. Sound waves that are too low pitched for humans to hear. That is not correct. They're too high pitched. So that means the answer is B. Sound waves that are too high pitched for humans to hear. But let's just double check by looking at A. Sound waves that are so loud they damage the human hearing. Again, like I said earlier, it has got nothing to do with amplitude and therefore loudness. So the answer is B. Next question. A student makes a list of some applications of waves. Medical scanning of soft tissue, sterilizing water, using sonar to calculate ocean depths. Which applications use ultrasound waves? Well, we did talk about cleaning earlier, not sterilization, but it was cleaning the object that goes into the fluid. So it's not going to sterilize the water, but it is used for medical scanning of soft tissue, including fetus imaging, and to calculate ocean depth. So it's C, it's 1 and 3 only. Which statement about ultrasound is correct? We'll start at the bottom. I have a lower frequency in audible sound. That's not correct. We know it's got a higher frequency and it's transverse. That is also not correct because it's longitudinal. There's a lower frequency in audible sound and there's a longitudinal wave. Well, the longitudinal bit's correct, but the lower frequency isn't. It has a higher frequency in audible sound and it's transverse. So it has got a higher frequency, but it's not transverse. So therefore, it has a higher frequency in audible sound and is a longitudinal wave. That is correct. So it's A. So the next lesson will be on diffraction, which I'll be uploading fairly soon. I'll post a link down below in the description. Thank you very much, everyone. I'll see you for the next lesson. Goodbye.